Click it. Got it. Okay. Okay, I think we're ready to go. Okay, so welcome everyone to the next Tuesday seminars here at the Warsaw University Astronomical Observatory. And today we have actually two speakers instead of one. Dr. Gudrun and Professor Gerry Gilmore are from the Institute of Cambridge, Institute of Astronomy, University of Cambridge. And we have been long-term collaborators on different occasions on Gaia and our plans. So, I'm very glad they accepted our invitation to come here and talk about the recent paper about lensing, something what we all like and are interested in. So, Gudrun, Gerry, please.
Well, thank you very much for having us. So Gerry and I will give you an overview of the early light bending tests of general relativity. And our talk is going to be in two parts. I'm going to give you a bit more of a historical overview and also talk about some later interpretations of one of the light bending tests, the one based on the 1919 Eclipse. And my part of the talk will be based, the slides aren't moving forward. Oh, is it? No?
Just click on the presentation and then slide down.
It's working. Right. So part of the talk is going to be based mainly on a paper that Gerry and I wrote together, which is called the 1919 Eclipse, which verified general relativity and its later detractors. And that was published 8 months ago, but 2 months ago it appeared in its paper version. So starting with the so the first two slides here are just a historical overview of general relativity, just to set the sort of the historical scene of events which form the background to the early eclipse tests leading up to the 1919 eclipse that we're going to talk about. So perhaps one of the more important aspects to highlight straight away is that as early as April 1912, Einstein visits Freundlich and discusses the possibility of astronomical tests for his theory of general relativity, envisaging eclipse tests as a possibility for verification of his theory. Again, I'll leave you to read the main parts of the history here. Here, perhaps the important point to highlight is that as early as March 1917, which is more than 2 years before the actual eclipse took place, Frank Dyson, who was the astronomer royal, already highlights the importance of that eclipse. The eclipse was indeed spectacular or particularly relevant in that it was going to be having a field of stars which was particularly homogeneous, very well populated and also particularly bright. So it's formed, it was just an excellent opportunity for tests like for verification, the possibility to verify general relativity. So just in the 3 simple steps of what the test is doing. So the first thing is the measurements we're taking of the and these simulations were measured while the field of stars was eclipsed by the sun. And then the 2 measurements were compared, and the differences and the apparent shifts due to the solar light bendings were deduced. One thing of note here is the picture on the right is an original historical picture from the 1919 eclipse. of the star which was closest to the sun. And the red arrow shows the Einstein displacement, which was eventually shown. So of an eclipse, or the type of test that was done, they can scientific purpose because they can vary, and they have varied in history depending on the eclipse. So, for example, in the 1919 eclipse, the test that was at the basis of it was a verification of which one of three possible theories was the most likely. So three theories was the one of zero difference, the one called so 0.87, or the Einstein deflection, which is 1.75. In the 1922 eclipse, it was more a case of verifying the 1919 results with more precision. In 1922, the Einstein theory was taken as verified, but or as basically verified, but new verification were undertaken simply with more precise instrumentation. In 1929, the case is slightly different, in that the enterprise is now no longer a verification of what is the most possible of three theories. It's already now accepted that the Einstein theory is the most likely. And what people are now trying to do is measure the deflection more precisely. And so it's now a question no longer of one of the theories. What is the deflection? So is it 1.75 or is it a different number? And the difference is actually is critical. I can't go too much of it into details, but perhaps the point to highlight is if you do a test to verify which one is more likely between three possible theories, the measurements that you need in order to achieve the verification does not need to be as precise as, for example, in the case of the 1929, where the whole purpose is to have an idea of the precise deflection. This is important because the two have subsequently been mixed up in later commentaries on the results of the 1919 eclipse. Alongside the scientific purposes, scientific methodology. So in 1919, for the 1919 eclipse, standard methods of measurements were used. The teams which went to the eclipse were very experienced in measurements in astrometry. But the resources for the expedition were very limited, and they were limited, you can see from the date. In 1919, it was just the year after the end of the Great War. So resources were depleted, instruments were not necessarily available, and nor were, if you want, the expertise or the manpower, because unfortunately, and that was the case at the Cambridge Observatory, the two colleagues who would have normally accompanied Eddington sadly were killed in action in 1917, so they weren't available for the expedition. Offsets. This is the very fortunate star field that I've mentioned before, and very bright and very numerous. In 1922, things changed a little bit, and the expedition is much better resourced, with specialist telescopes being used, and as a result, the measurements being more precise. Still, the techniques used are the proven techniques, and there are many cross-checks that were made in order to carry out the verification. In 1929, it's again a different picture. The team for the 1929 eclipse is relatively inexperienced, as are the techniques And the assorted techniques were also as yet unproven. The star field, which was the star field at this eclipse, was considered at the time to be slightly suboptimal in that there was only one star on one side of the sun, while the rest of the star field was on the other side of the sun. However, Gerry will talk about the 1929 eclipse a little bit later and actually show that, in fact, the star field wasn't as relevant to the results as it was originally assumed at that time. So now to the 1919 eclipse in particular. So short description of the team. So Arthur Eddington, obviously, in the lead of the went to Principe with Edward Cottingham. Edward Cottingham was a clockmaker in Cambridge, and he was known to the Cambridge observers because he also, I believe, had a contract to look after the astronomical clocks in the observatory. So why did Eddington go accompanied with a clockmaker? Well, partly because of the post-war consequences that I've already mentioned, that other staff, which would have been more experienced and perhaps more likely to go, were no longer there. And also, the reason why a clockmaker was chosen is that he would have been extremely experienced with precision instrumentation, which was an extremely valuable expertise to Eddington. Eddington obviously had his expertise as an expert astronomer. The other two in the team, the other team was formed of Charles Davidson and Andrew Cromlin, who went to Sobral. So Davidson and Cromlin were themselves academic of very high reputation. Davidson was a mathematician, Cromlin was a very expert observer. And then we have Frank Dyson, who was very much involved in the preparation of the expedition, as we've heard of his name before, and also, again, very much involved in the evaluation of the results, but he didn't actually go physically on the expedition. So the eclipse took place on the 29th of May, 1919. So the two teams went. Three sets of measurements were taken. One measurement was taken in Principe and two measurements were taken in Sobral. So the measurement in Principe was taken by a telescope, and in Sobral there was one measurement taken by a telescope and one by an astrograph. Importantly, one of the measurements of one of the Sobral instruments, the astrograph, was known at the time of the eclipse. The instrument itself was known to have undergone significant changes during the eclipse, and therefore the observers on site had already wondered whether the data would be actually safe to use, whether it would not be riddled with too many errors to be usable. Eventually, it was decided that the astrograph results should be discarded. From Sobral and one set of measurements from Principe were presented on the 6th of November 1919 to a joint meeting of the Royal Astronomical Society and the Royal Society at Burlington House in London. So the nature of the societies and the place will tell you that the team presenting the results, Dyson, Davidson, and Eddington, also had an audience of extremely knowledgeable people. So they presented their results to people who could actually evaluate both the method that had been used and also, more importantly, the reasons why Eddington and Dyson would have decided to discard the measurements of the astrograph. So based on the two data sets that were presented, it was clearly shown that the results favored the Einstein prediction. So of the three possible theories, it was concluded that the Einstein theory was the most likely. Importantly, there was no immediate criticism of either the results presented to the audience at the time, nor of the method for obtaining them. So nobody questioned Eddington's projection of the astrograph results. As a result, the Eclipse results were made the next day's front pages, and they really made Einstein famous overnight. So these are a few of the front pages of the time. It was big news. So what came next? So in terms of the immediate history, in 1922, expedition was organized, which was, as I said, much better resourced with much more precise instruments, and the results of the 1919 expedition were indeed verified. And in 1929, the attention turned to something a little bit different, where the enterprise was to measure the deflection much more precisely. So was it 1.75 or a different number? But what I will focus on next is, so I'll make a little excursion into a later interpretation of the 1919 eclipse by a different set of people who are historians, philosophers, sociologists of science. Because as some of you might have come across later, later portraits of Eddington, where Eddington ended up being accused of having faked the results of the 1919 eclipse, and rather than, as we have seen now, presented them in good faith. So the paper that Gerry and I wrote was based on the question: how did the reputation of Eddington came to be altered in this way? So where did the accusation of having faked results come from? And what we found was that it was basically all originating from a paper which had been written by John Earman and Clark Gilmore in 1980. And based on that paper, from the decision to exclude, as I've just said, one set of data, Eddington's reputation went to debasing the whole scientific enterprise and faking results. So how did that happen? So Earman and Gilmore wrote the British Eclipse expedition of 1919 and their predecessor, which sounds like a sort of overview of eclipses. But in fact, there was another purpose to their paper, which is explained in the first box in that blue box. Namely, that until Earman and Gilmore, it was generally thought that the British eclipse results and the British discussion and assessment of relativity that preceded and followed had been offered as an example of a scientific revolution carried out rationally and without nationalist prejudice or obscurantism. And so you can say that, you can see from that statement that we are now in a sort of philosophical debate about what a scientific method should be or could be. And what Earman and Gilmore effectively did was to undermine the statement in the blue box. That was we believe, the main purpose, or one of the purposes of their paper. And how did they do that? So they attacked a number of the premises on which the expedition was built. Partly they even attacked the trichotomy that I presented as choice of three possible theories. But the main argument that they presented was that the decision that Eddington made graph data set was based on bias. and that he did that because he knew that the other data sets would favor Einstein's theory, and the argument was made that he already wanted that theory to be favored, and therefore made the decision to discard a data set which, if considered, would have not provided, according to Ehrman and Gleimer, would have not provided as determined a result as was possible without that data set. To make matters, I suppose, better for them, but worse, in fact, Ehrman and Gleimer then undertook to reanalyze the results that Eddington, Dyson, and their team had obtained. And they claimed that if the data sets, the astrograph, first of all, they claimed that the astrograph data set should have been included. There wasn't actually reason not to include it. And if it had been included, it would have shown less conclusively that the Einstein value was the one, or that Einstein theory was the most likely one. So, what Gerry then did was to do exactly the same thing again and reanalyze the results from the historical results. And Gerry found that not only did the experts of 1919 make the right decision, but Ehrman and Gleimer actually made a mathematical error in their own reconsideration of the data sets, and which undermines really their whole argument against Eddington and the team of 1919. Nonetheless, I might as well discard this one. Nonetheless, their argument found its way to imputation. First more important piece of that it went into was Collins and Pinch's Golem, What You Should Know About Science. That's a very sort of popular publication, which is extremely successful. I don't know how many editions it had been, but it's an extremely successful, very popular book, which claims that science is not necessarily always a rational enterprise, but riddled with possibilities of bias. And here already, what Collins and Pinch did, it was simply to take over uncritically Ehrman and Gleimer's arguments. They did not re-examine the arguments, so they did not look at the mathematical part of Ehrman and Gleimer's arguments, but simply decided that, slightly bizarrely, Ehrman and Gleimer had become the new experts of the analysis of results, which had been previously analyzed, one would have thought, by experts of greater expertise. After the Golem, the arguments found their way into, for example, John Waller's publication, Fabulous Science, so that tells you everything, fact and fiction, in the history of scientific discovery. And here really the claims become more and more forceful, and also less and less based on really verification and expert argument. So here we see that the claim is made, as science historians John Ehrman and Gleimer have shown, the evidence they presented, they meaning the team of 1919, was unquestionably inadequate. And that Eddington had served to debase the whole scientific entity. So you can see how history is sort of turned onto its head, where the historians of science and of the time who were really become the people who cooked the books. So this sort of culminates in other experts, and where those results were endorsed. And we now move to a situation where people of arguably lesser expertise scrutinize this endorsement and question the expert's expertise. And using a form of discourse which becomes progressively less evidence-based and less demanding of expert scrutiny. But it still has as its main objective the questioning of the expert's expertise, which is slightly self-serving, and it also shows that, that actually the people who first raise the question about the expertise are guilty of exactly the same thing. Ehrman and Gleimer's argument relating to Eddington's bias was based on two things. First of all, they claimed that there was scientific bias, that Eddington was already convinced of Einstein's theory even before the experiment, the expedition was organized. The second claim of bias was political, and I suppose it's a claim based on conviction. Eddington was a Quaker. He was very much a pacifist, and he shared that with Einstein, who was also very much a pacifist. Both men, I think, believed in what I would phrase as the fact that science should transcend nationalism, consideration of nationalism. And they were both very eager to reconnect the scientific communities which had been divided by the Great War, so the British scientific communities and the German science communities. So both of these statements, the scientific, if you want, scientific convictions and the political conviction are both true. But in order to mount an argument claiming that Eddington would have been biased in discarding the data sets of the Sobral astrograph, you would have to add another argument, which is that Eddington would have foregone his scientific integrity in order to accommodate his other beliefs. And that's not an argument which is actually that easy to make. And that's an argument that we hopefully, in the paper that we have written, have demonstrated was not the case. So I think this is a good place where, Gerry, you could take over with the sort of more mathematical and statistical.
Thanks, Gudrun. We have some questions at the end. So now I'll go through in a little more technical detail of what happened in these analyses and in the statistical context of the time, which is particularly interesting. So what I have here is a list of the eclipses of the time, all of which were designed to test general relativity. And so the first test, you can actually see with hindsight, they went back to the turn of the century and reanalyzed existing eclipse plates. But the first attempt specifically to test relativity was by Perrine from Cordoba, who went to Brazil and it rained. Then there were three big groups, Freundlich, the Lick team, and in fact a Cambridge team and a French team, who went to Crimea. Unfortunate timing, they all got arrested at the beginning of the war and their equipment was locked away, but it was cloudy anyway. In fact, the Cambridge team was only about 1 kilometre from where there was a successful French team, and the Cambridge team chose, this is Newell, not Eddington, chose their spot so that they had a good access to a good place for dinner. So that was a bit indulgent of them. That was jointly with the Potsdam Freundlich team. Anyway, this was the time when the high quality telescopes were locked away during the war, and so were not available at the end of the war part of it. But then you see it was cloudy all over the place. In 1918, in the US, there was an expedition, but the equipment wasn't there and almost none of the people were there because they were all on war work. And so there was a experiment, a light bending eclipse, which never produced any results in the end because it wasn't, the telescope wasn't well enough put together and calibrated. So then we get to 1919, which was the first time when results were actually obtained, a decade after they'd started. And then again in 1922 with this mega expedition down into Australia. Then the next expedition, again cloudy, and then by the last of this sequence was 1929. So you can see immediately from that list that the most important way to test general relativity is to be lucky, because it's eclipses happen where they happen, and they're very rarely in good observing sites, and so you usually are in trouble. The other thing is eclipse expeditions are expensive because you have to move your observatory. You can't move the eclipse. And so here's a picture of the fact the 1922 Lick expedition to Australia. They took down 5 telescopes with the mounts and the drive and the whole thing. They shifted the entire observatory down to the desert in Western Australia. The picture there is of just the American scientific team. There are roughly twice as many local people there as well, helping out, largely provided by the Australian Navy. So these were mega expensive things, and they took half a year and were major scientific projects. By contrast, the 1919 one was just at the end of the war, and they didn't have the telescopes, they didn't have the money, they didn't have the people. Everybody was still in the army at the time. And so what they had to do was lash up, and they took 2 horizontal telescopes. This is the setup in Brazil, in Sobral. And they fed them by coelostats. So the only moving components were these coelostat mirrors, and they knew that was the weak point that they had to worry about. And it was tuning those was the reason the clockmaker was taken to Principe, and 2 experienced people went to Sobral in Brazil. And the larger of those telescopes, the one on the left, is the famous astrograph, which produced the distorted images. And when they took comparison plates just a few hours after the eclipse later that night, the local observers immediately realized something had gone wrong, probably heat distortion. So they waited there for 2 months to take comparison plates with the same distorted equipment. And I'll show you in a couple of slides why that was necessary to try and do what they can. But basically this was a lash up on the cheap. And so it didn't have all the trimmings of a full-blown expedition. So here again is the context from 1922. This is actually a 1940s picture of the Cambridge Observatory. So it looks rather like here, actually. Big old building and nice trees and things around it. But you can see the people. What it was 3 institutions. There was a large solar physics observatory that had only just arrived and was run completely independently from the Cambridge Observatory, which is the big old house. Half of that was the director's house, still there. And of that team, the only survivor of the war was Eddington. And then also, people forget this, on the lawn out here, these funny little radio aerials, that was the meteorological physics site run by C.T.R. Wilson, who was interested in studying cloud and famously invented the cloud chamber, for which he got the Nobel Prize. But that was in the gardens, that wasn't in the observatory. So the process of an eclipse experiment is really very simple. You take your comparison plate, your eclipse plate, you put them together and you measure the differences in positions. So the data set you have are these small differences in positions of the stars. And what you then do with it depends on how you're doing the experiment. So in a general astrometric fit, in a moderate accuracy experiment, you would use these standard Seidel distortion correction equations. So you'd go up to 3rd order. And that's the sort of routine thing that one would do if you have a field and you have a telescope that you know is imperfect. The methodology that was used for differential astronomy, and this is critical because it's differential astrometry that actually delivers, as we now know with Gaia. The idea of differential astrometry is you fix everything you can fix and only allow small 1st order perturbations. And so if you don't move your telescope, you just compare 2 pictures taken at different times, then all the high order terms are going to be almost identical and you can ignore them. And that was why they stayed in Brazil for 3 months to take another set of pictures with the same telescope without moving it. As it happened, that didn't help anything. And so that is how they deduced that it must have been the temperature change, not a physical change that was the problem. But the normal set of equations they used were just these simple low order things. And this they'd learned how to use very accurately from parallax studies over the previous 25 years. And here, interesting, is a little historical note. Here are those same equations from the lecture course that Eddington gave after he came back to Cambridge. He taught this as a standard lecture course. There are the equations up the top. And these lecture notes, and this puts it in nicely in context at the time, were taken by a student called Egon Pearson. And Egon Pearson later became professor of statistics at London. Egon Pearson's father was Carl Pearson, who invented many of these statistics in London, with his colleague Jerzy Neumann, who I'm sure I mispronounced, but anyway, he was Polish. He was also working in London at the time, and Fisher. So the standard methodologies we use these days, matrices and Pearson confidence tests and so on, were being developed during the 1920s and 1930s, mostly through very bitter public arguments between those four people, but all in London. And so none of this was established at the time. And so none of these statistical methods were either known to or used by astronomers during the 1920s. And that's important. We have to look at what they did in terms of what they knew, not with hindsight. So looking at what they did, first thing we did, they did everything by hand with these probably Brunswiga calculators and God knows what. But anyway, first thing we did is check their arithmetic, and sure, they got their arithmetic right. So in the main column down there, we have the calculations that they produced from tables of numbers that we have available. And on the right-hand side is what happens if you do a standard modern least squares fit using standard Python codes. And they agree. There's the odd occasional rounding error, as you would expect, and the odd typo that we spotted, but the arithmetic was perfectly correct. These people were able to calculate. So then there were three sets of data from 1919. And the latest statement was the errors were as large as the effect. One sees this statement quite a lot in the post-1980s literature. So let's go and look at what those errors are and what the corresponding probabilities are that the three conclusions that one might draw favoring null, Newton or Einstein are correct from the three different data sets. And as you can see, the top one, which was the most favored by Dyson, strongly favors Einstein and strongly disfavors Newton and null. The Principe astrograph results from Eddington moderately favor Einstein and mildly disfavor Newton, but not much, but you put the two of them together and that's stronger. Whereas the data set they removed is neutral. It is so uncertain that it doesn't provide any information. And that was why they threw it out, as they said. So that's what they did was entirely reasonable with the mathematical knowledge of the time, and in fact with hindsight as well. And so then we can look a bit harder and say, well, what came next? What was the real accuracy and results that came up? So the statistics they use at the time are not common to us. They're called probable errors. So we've converted them into modern standard deviations. So the errors look bigger now. And so the second column there in modern terminology is the accuracy of the two results. Then there's the dispersion of the data, and you can see that gets quite high for the Sobral results. There's the mean and the error on the mean, which is 100% for Sobral, consequence of zero weight really, not single weight, and the internal dispersions. And so when you look at those data, you say, well, what's going on with Sobral? And Dyson himself said, well, it's clearly a systematic error has happened in the Sobral. Let's assume that systematic affected only one parameter and not the other. And then I double the answer. So there's a systematic error of 100% on these data, and that is why they didn't use it, which is very reasonable in the strict sense of the word. However, Erling Gleiman then said, well, actually, no, this isn't right. So what did they do? Well, they said the internal dispersion of the poor data set is the same as the quality of the data from the Principe astrograph. And what they did was confuse two completely unrelated things, because they messed up their statistics. And so they see from this, you can see in the columns in this plot here, in the third column, the dispersions, and the dispersion of the Principe astrograph is nearly half an arc second. And then on the second last column, you can see the internal dispersions, which is before you allow for any averaging and so on. And there, the same number appears for the Sobral astrograph. And so they just simply jumped across those columns and said the bottom number in the second to right column is the same as the second. And so they completely overlooked systematic errors, making that comparison. pages of the report published by Dyson Eddington was all about systematic errors. Almost the entire report talks about nothing but systematic errors. And they completely overlooked that. So they made a simple, you know, it's not, you wouldn't even call it an undergraduate mistake. It's just a simple blunder. And so that's the entirety of their evidence. And it's such a grossly obvious blunder that when I read through their paper, I remember reading through the paper, it took about 30 seconds before I said, hang on, this number doesn't make sense. And I remember walking into Gudrun's office and saying, you'll never believe what these people have done. And so you have to deduce from that that nobody familiar with elementary statistics had bothered to read Gilmore&G.Tausch-Pebody paper in the last half a century, or they would have spotted it. But anyway, there's also that they then go on misusing statistics and saying, well, let's just put them all the data anyway together just and see what happens. So you can do that. It's an artificial thing to do because you have to assume that there's a Gaussian distribution function corrected for an offset 0 for Sobral, so it's not a robust number, but you can do it according to the methodologies of the time. And this is the result that you end up getting. And so you end up, bizarrely, finding that the agreement with the Einstein prediction actually becomes stronger. So the precise opposite of what they said is the conclusion of their own mathematical error. So not only made a mathematical error, they got the deduction from that mathematical error backwards, which makes one suggest that a bit of peer review of that issue might have been of value. They did one other strange thing. They said that actually Einstein didn't know how to calculate the value of the light bending. And he came up with this rather iterative, complicated methodology, which it is an iterative, complicated methodology. But Gilmore&G.Tausch claimed that Einstein's method couldn't actually be trusted until you had a result that proved that it matched the prediction. And therefore, there was an iterative prediction demonstration. Now, this is a very, very strange thing for any historian to do, because anyone who knows anything about general relativity knows that only 4 weeks after Einstein developed the final GR paper, Schwarzschild produced the Schwarzschild metric. So it was 4 weeks after, and this was 2 years before any of this appeared in the West. So just 4 weeks later, Schwarzschild produced the Schwarzschild metric and wrote in, this is the translation of Schwarzschild's paper from January 2016, that in fact, not only is Einstein's calculation unique, but it's also accurate. So there was never any doubt at all that the method, the result was correct. And so we don't understand at all how this issue about the prediction could even have ever arisen. That it makes up about a half of the article in the Golium, the Collins and Pinch article. There's about half of the cases that no one knew what the answer was until they measured it. So it's very, very strange how these things run out of control. Now, we'll end with just a couple more interesting things about the statistics of the time, because we don't want to just suggest that the statistics were fine. Here is the set of results from the 1922 Lick experiment. They took 2 telescopes, a big one, 15-foot focal length, and a stubbier wide field one, 5-foot focal length. There are the 2 results they got, 1.72 and 1.82, were quite small probable errors of 1/10 of an arcsecond or so. So they claim to be quite precise. And then the average comes back to the prediction with a very small error. And you think, well, given the challenges of doing these experiments, is that agreement actually too good? Is it plausible? And so this then, nobody, again, as far as I can tell, no one has ever re-reduced the 1922 data. Now, this can't be right because it's such a giveaway undergraduate experiment project that it must have been done by thousands of undergraduate students all around the world, thousands of times. It's just no one's bothered to publish it. So it's quite interesting then, with our perspective on statistics, is to say, well, what actually happened in the Lick data sets? Well, here are the results from the good high resolution data, the 15-foot, and there were 2 different people measured it, W.W. Campbell and Trumpler. Both the experts. Campbell measured 3 plates, got 3 separate results. They're on the left with a mean 1.60, but quite a high dispersion. And Trumpler measured 4 plates and came out with a spectacular mean and quite a small dispersion. What they then did, in spite of the fact that what we have here is 2 sets of correlated errors with systematic offsets between them. They just averaged the whole lot with some sort of internal weighting, and magically ended up with exactly the right answer. Now, perhaps it's surprising to me that people didn't comment more on this at the time, and it's surprising that perhaps Seaman and Gilmore didn't have a look at this. They might have had more fun to play with this. But anyway, they did recheck the numbers, they did their arithmetic correctly, but the fundamental statistical methodology underlying this is marginal at best. So then what happens with the next the set of lick results, and that was the 5 foot, so the wide field. So you can see a picture of the field up there, hundreds of stars spread over a very large area. They were looking for a very, very small effect on a large number of stars here, because most of the stars are a degree away from, and the amount of light bending is tiny, so they're having to average over a lot of stuff to see anything. And the results that they published in detail are listed there. And if you just look at the first list of results, the Lick deflections, Einstein deflections, you see they range from, or just look at the bottom two, they range from 1.0 to 2.5 arc seconds. And so out of a sample of 6, you've got a range of 1.5 arc seconds when you're looking for something, and they claim with a sigma of 0.2 arc seconds. So if you, down the bottom left there, we've just plotted the numbers as they presented them. And the dashed line through the middle is assuming their means are right. What is the standard deviation of those numbers actually look like if they fit a Gaussian distribution? Because there's no way they fit a Gaussian distribution. 3 of their 6 points are outside 2 sigma. So the true Gaussian is about a half an arc second. So although they claim they're measuring things at 0.2 arc second, a half an arc second is the minimum. So they're actually much worse than they think they are. But then amazingly, with that, they average everything together and end up with almost exactly the right answer again in the mean. So we'll come back in the last slide to that. Now we'll move on to 1929 and poor Mr. Freundlich, Erwin Finley Freundlich. He was famous because he was the first supporter of Einstein. He was a theorist who was given a miserable data processing job in Berlin, working on the sky survey, doing a crude astrometry. But he was so bored, he was actually skipped off much of his time and spent his time supporting Einstein from 1911 on. And he worked on, first thing he did was looking for the gravitational redshift in stars. Now this was very difficult to do, of course, because you don't know the actual velocity a star has. And so you're trying to look for a small GR term on top of the actual random velocity of the star. And this was, you had to do guessing stellar densities and things, which they didn't know anything about at the time. And so he ended up with huge arguments with his local colleagues on Seeliger and Ludendorff. Ludendorff was not the sort of person you should have had an argument with, because he was not only the local director, his brother was the deputy head of the German army, who later became the German president and the person who put Hitler into power. So Ludendorff was not a random person, and he was a brave person who picked an argument with him. And he described Freundlich science as wishful thinking in the literature. Of course it was, because stellar kinematics at that time was just being developed, and here's the references here, and Freundlich doesn't mention any of that. So he knew nothing about the way stars were actually moving, and was a rotten experimentalist. And he was terribly unlucky with his eclipses. It took him more than 20 years for he got his first fine weather one. And this is it. This is what happened. And he didn't use a standard methodology either. He decided that the biggest uncertainty in producing results was the scale of the plates. And he was right, and you'll see that on my next slide. The scale is the maximum, the dominant term in the astrometric fit. And he decided that he wanted to fix this independently by projecting a graticule grid on the eclipse plates. And that didn't work, and it didn't work with hindsight. Well, he was told at the time it wasn't going to work by all the experienced people, and it didn't work for what today we would call non-common path errors. So he had to have a third telescope feeding light into his eclipse telescope, and that third telescope was itself being affected by the change in temperature and gravity and everything else. And so there were too many non-common path errors, and so it's a methodology that in principle can never work. but nonetheless, he did it. And what he did then was get these 4 results. And again, huge dispersion, but with a very high mean, 2¼ arc seconds. And then he quoted this very small, and it's very easy to work out what the probability of this range of numbers is, given that, and there's less than 1 chance in 10 to the 8th that he was right. And 1 or 2 people commented on this at the time, including Einstein, who wrote to him and said, surely your errors can't be right. You know, this seems a very disturbing range of uncertainties, to which he commented, as you can see there in italics, this was in a reply letter to Einstein, oh, fundamentally data are always twice as bad as we say they are. And that even by the standards of the time, that was rather lax. But anyway, people didn't like his result of 2.24 because by now, general relativity was the paradigm and you needed good evidence to prove it wasn't right. And so this is a consequence of Gudrun's point. By now, the psychology had inverted. So instead of having to prove that light bent consistent with Einstein, you now had to prove that it didn't deflect consistent with Einstein. And so all the bias was the other way around. And so people didn't like his result. They went and reanalyzed it in a variety of different approximate ways and got a variety of different answers, which tells you something about how subjective were the analysis methods of the time, that you can get 5 quite different answers from the same data set, just depending on how you do it. But anyway, we did it properly. This is the famous asymmetric star field that Freundlich had. So you can see there's only one star on the left-hand side there and a bunch on the others. And on the right-hand side is again the distribution function of Freundlich's errors, and they're clearly not remotely consistent. You've got 4 points and 2 of them are out at 4 sigma, so they're clearly not remotely consistent with any plausible Gaussian-like distribution function. And so we can do it. We have our numbers, so we can re-reduce them. And so we did that just by bootstrap resampling and said, okay, what are the sensitivities to these various things? And it turns out the star that's sitting out by itself was not actually the problem, though everybody thought it was at the time. It just looks funny, but statistically it isn't. It's actually quite robust because it's about the average distance of the stars from the sun. The fact that it's left-right on the plate makes no difference because there's no left-right turn in the fit, so we're not allowing for that. So it makes no difference. It was an interesting example of how they got it wrong. But from this bootstrap sampling, you can see the sensitivity to the different data points, and we've plotted those there in the box on the right, where the vertical axis shows the relative change in plate scale and in deflection versus the plate scale. And so you can see there's a great correlation between the top left and the bottom right. And so Freundlich was right that there is a degeneracy between plate scale and derived deflection. It's just his methodology wasn't able to manage it. Whereas the standard way of reducing the results actually contains enough information to determine the scale. And so that's what Trumpler then good old Trumpler again, came along and did. He was on holiday home in Zurich at the time, so popped over to Potsdam and reanalyzed. He didn't remeasure the plates, he just re-reduced the data. And so he got a new result, and this is it. And so this in the third line here, the Potsdam result as analyzed by Trumpler is 1.75 arc seconds with a coded error of 0.27. And so now we're left with this interesting point, is that the person that history trusted, Trumpler, later became a master of statistics, of course. Trumpler and Weaver, the book on statistical astronomy, is where I certainly learned my statistical astronomy from. But if you look at his determinations of light bending, you find that they're suspiciously, perhaps, or at least surprisingly, close to the final prediction. He always gets it exactly right, even though his data have got the same huge dispersion as everybody else. So was he just lucky? We have no way of knowing. But his arithmetic was certainly right. He did actually, and the 5 and 6 plates with a huge dispersion do actually correctly produce the Einstein deflection result when you measure them. It's just an amusing little anomaly. So, final conclusion, following on from the conclusions about society. So, there's this question of expert and standard methods. The methods, the statistics they had at the time, were by our standards very primitive. but the technical expertise they had in measuring what we would call microlensing, that term was actually used in 1911 and then forgotten for 30 years, but it was around at the time. And so the methodologies then were checked and accepted and supported. In the context of the time, that worked. The non-expert astronomer wasn't accepted for two reasons, but the first of those reasons was that he didn't match people's preconceptions. It's a fair assumption that if Freundlich's flawed methodology had ended up agreeing with Einstein, no one will bother and look again. So we end up in this vicious approach of who is accepting as expert whom and why. We as physical scientists tend to overreact perhaps to people like Ehrman and Gilmore and Collins, who say that everything we do is entirely subjective. They don't believe there's anything objective about science at all. We invent what we call science. Now, we tend to think that's ridiculous because it's not expert. And yet we have our own subjective influences in what we decide is expert as well. This may seem like a purely internal philosophical over dinner glass of wine type chat, but actually this matters because the concept of an expert became very prevalent during COVID, where people argued about vaccines. Who was an expert on vaxxers and anti-vaxxers? It's been around for a long time in climate change, and we're seeing a current example with the history of Central and Eastern Europe. Who is the expert? Who is rewriting fact? And how do we respond to that? And to what extent are we going in with our own set of preconceptions? And to what extent should we try and step back and look at things objectively? Thank you.
Thank you. Thank you very much. That was an important message to deliver. Questions, please, to Gudrun or Gerry. Alec.
I read about one more argument against Eddington's result. And that was that before he left Freundlich and returned to UK, meaning before he took the reference plate, he claimed that the plates they got already, he's sure that they confirmed the Einstein prediction. Can you comment on that?
Yeah, as it happens, we did look into that and found the answer to that question. It's in one of our spare slides somewhere. Here it is. Yeah. So that statement, this is a picture of Einstein and Eddington, the only time they met in Cambridge at the observatories in Cambridge. Sadly, that chair's not there. The text that's written there was from the first announcement by Eddington of what he thought the results were, which was a postcard that he wrote. In those days, people were civilized, and when they made a discovery, the first person they told was their mother. Exactly the same thing happened 3 weeks later when this rumor got to Einstein. And the first thing Einstein did was write a letter to his mother, saying he heard it was true. What actually happened was just that he process to the very high quality. But the origin was one example, which
it all wasn't so sure. Was Freundlich the only one who was doing a big observation during the 1929 eclipse? Or were there other astronomers? It wasn't just that big of
Yeah, there is a. Shall I answer this one? Yeah, there were a total of about 30 attempted light bending eclipses through the 1920s. So, for example, at that 1922 project in Australia, there were 5 other eclipse teams, as well as the Lick Observatory went there. 3 of them chose the wrong site, and it was cloudy, and they got no useful data at all. And the other 2 was a Canadian team, and I've forgotten where the other one was from. They had rather poor equipment, and they got very, very results with huge error bars. And that carried on through the 1920s. There were very few results through the 1920s. Very few people tried. That the 1929 eclipse, which was in Sumatra, there was another group went off to one of the other islands around there at the same time and came up with, again, a very uncertain result with huge error bars. And then through the 1930s, there were 2 Japanese experiments that, again, came out with error bars that were more than 100% on their result, and a Russian one that was even why I've not found a translation of that. I don't know what uncertainty was 2 arc seconds on the results, so it was not much use. Then nothing much happened until the 1950s, when people started doing these experiments again. Through the 40s, there were obvious people had other things to worry about. In the 1950s, again, US teams started trying to measure things, and they got terrible results. So there were teams from Yerkes and Texas, and they got very poor results. And at that stage, people just abandoned the results altogether. So no one was ever able to reproduce the derived and quoted accuracy of the 1922 Lick results. That's a real standout. So Trumpler, it seems you can't get the right result unless you've got Trumpler there on your team.
Okay, that's really interesting. Thank you.
Okay, thank you. Any other questions? I just have a quick one. So you showed the stars, but in general, how many stars were used in each of those experiments in the Eddington itself? So you said the stellar field was very generous in stars. Was it somewhere in the galactic plane? And how many stars they used? Yeah, no, the 1919, it's all relative to the telescope and the photographic emulsions they had available. 1919 was on the corner of the Hyades cluster. Nice. And so that's the most extreme high density bright star patch on the entire solar ecliptic. So that was the perfect day on which to do it. But even with that, they had, I think, 9 stars. And that's because they needed the magnification to get the sensitivity. and because of the equipment they had and the size of the photographic plates that were available, that meant a very small field of view. And so they only had 9 stars. And on half of those plates, because it was partly cloudy, they had only 5 stars, which is the minimum necessary to actually solve the equations. So they took about 40 odd plates, and about 30 of them were useless because there weren't enough data sets. And so that was the typical, was somewhere like 5 to 10 stars was typical. The exception was the 1922 Lick people, where they went for the opposite extreme. And so instead of doing a small number of high precision points, they went for a large number of lower precision points. And so they went for the wide field, and they took just 1 plate in each eclipse. So they integrated with the whole 4 minutes and just risked everything on the one. To get more stars. To get more stars. So in those cases, they had about 100 points. Nice. And they were the only people who ever tried to do it like that. Everyone else went for the small number of high precision data points. And that's very hard, clearly, to do. Sure. Okay. Okay, thank you very much. I don't see any more questions. So let's thank our speakers again. Thank you for coming.